All right. In terms of where we left off last, we started talking about measurements using our making a rainbow lab. And in this case, we're just going to start to complete the rest of the section about measurements on the note sheet. And then we're going to get into some calculations and using measurements to help us out with that. In this case, when we're reading the graduated cylinder, now remember, all of these are on the slide deck that's also posted on Schoology. But in order to read a graduated cylinder, what happens is graduated cylinders are used to measure liquid amounts. And liquids tend to have this little curvature shape at the top when you're measuring. And that's what we read at eye level when it's on a flat surface to be able to accurately measure the amount of liquid in some type of graduated cylinder. So we read this part, and we'll keep reminding everybody, but this is what we call the meniscus. The meniscus is just that bottom part of that curve at the very top. It's not as drastic as you see here, but it's definitely noticeable when you're looking at it. So everything, like we said, determine the value of each mark on the graduated cylinder. In order to make an accurate measurement, you have to be able to know what does each one of these hash marks represent, right? So what increments does it go up by? So how we figure that out is we look at the values that we do know and then figure out, okay, well, based on how many hash marks there are in between, what must they represent to get from that whole number to the other whole number that we know. So as I can see here, it ends up being going up by ones, right? And this one is 3, 4. So if we tack on whatever the tens number is before that, we end up going up by ones, getting into this portion, which is a little bit of a longer line. That's usually the halfway point between two objects or two lines and two whole numbers that we can see. There we go. So in this case, when we're making a measurement, we're measuring liquids. So when measuring liquids in a graduated cylinder, you want to set it down on a flat surface or desk. Our lab tables will be just fine for that. We want to read the measure at the bottom of the curve, which we just said is the meniscus. Lower your eyes to eye level. All right. Now, why eye level? Because if you are looking at something maybe from an angle up here, you don't see that full accurate measurement. It's a little skewed. We kind of talked about that in our optics unit. So eye level, so you can actually make an accurate reading. And then you want to include, and this one's important right here, include 1 digit of estimation in your measurements. Now, that means that when I make a measurement, I know that I have a value that I know for sure that I can read, and then I go off of that here. So in this case, based on where this meniscus is right here, we see that that meniscus is pretty much in line with that hash mark there. And that hash mark represents, based on our increments, 26 milliliters. So in this case, I would say that this is 26 because I know that for sure. And now we're going to give an estimate. The cool part about when it's on the line like this or real close, your estimate can actually just be 0, right? And if it were like, let's say the meniscus was actually right here, which was like right in the middle, this would probably be like a good estimate of 0.5, so on and so forth. So an estimate is your educated guess. So in this case, estimations aren't really going to be graded necessarily as long as they make somewhat of some sense. So we're going to say that that's about 26.0 units, of course, are important, and it is milliliters for our volumes of liquids. So a couple of practice problems here. You can do the bottom 4 on your own if you want, but we're going to just go through here, reading the meniscus and such. Make sure that you know what the increments are, right? Each line represents 1 whole milliliter based on the numbers that I can see there, 110, 120. So I'm reading at this point right here. So I have to figure out, okay, where is that between? And that is between this line, which is represented by 115 milliliters, and between this line, which is 116. Now, it's not quite at 116, so we say, okay, well, I know it's for sure 115, and remember, that last digit is an estimate. So wherever this represents, now we can see that it's not on the 115 milliliter mark, which means that we can't use 0 as our estimate. That wouldn't make much sense. But we do see that it's a little bit past it, and it's not quite in the middle, so it might not be 0.5. So you can put, I don't know, let's say 0.2 milliliters, right? Or 0.3. So there's multiple kind of correct answers there in terms of how we're doing this. For this one, very similar boat. Each mark represents 1 milliliter. And because of that, I know that it's just past, and this would be 57. It's just before 58. So my number that I know for sure is 57, right? It hasn't reached 58 yet, and that last decimal, that's some type of estimate. And again, kind of looks closer to 57, so you can say 0.3, you could say 0.2, does not matter necessarily. In this case, we see it looks like it's on the line. We see that each mark represents 1 milliliter again. So then we can say, all right, well, I have a number at this line of 66 milliliters. And that means that if it's on the line, my estimate is 0. And there we go there for our measurement. And over here, we have increments of 1 again. This meniscus looks like it's right in the middle between 39 milliliters and 40. So we're going to say 39, and if it's right in the middle, 0.5. So again, you can do the other ones as extra practice if you want. Another way to identify the increments is to this is more mathematical, and you don't have to do this. You can just kind of guess and check. But you notice that you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines to get from one thing to another. So there's 10 lines, and you can just divide that value by whatever the difference is between these two. So 40 minus 30 is 10. So we take that 10 and we divide it by the 10 lines it takes to get from 30 to 40, and that's how you can see that each increment is 1. But that's more mathematical. You don't have to do that, but it does kind of make it a lot easier, a lot nicer if you do want to do it that way. So measuring is very important in chemistry. What part of the liquid? The meniscus. All right, now density is a relationship between mass and volume of an object. So we said that mass and volume, if anything has mass and volume, it is matter. So we can actually identify what those quantities are in relation to each other to then have like a little mathematical representation. So what you'll see here, density equals mass divided by volume. We can just abbreviate that, D equals M over V. And we know that we have our nice little trusty triangle. And remember how to use these. If you want to solve for something, let's say I wanted to solve for density, I cover it up, and whatever it tells me to do with the other two, that's how I can solve for that particular variable. So an example calculation, I forget off the top of my head what the actual problem was, but I believe it was solving for volume. All right, so you know what? Let me go back into the note slides, and then I will double check just exactly what that calculation was. So very good. So here we have density equals 10 grams per centimeter cubed. Now, centimeter cubed and milliliter is basically the same thing. The difference is centimeters cubed is for solids and milliliters is for liquids. Mass is 40 grams. So because I have this information and I know that this is my original equation, I'm going to use the triangle to cover out volume because that's what I want. And I see that I need to take my mass and actually divide it by the density. So I'm going to take this equation right here and I'm just going to rewrite it. And I'm going to use this equation instead. All right, so it's the same equation that we're using for density. The difference is now we have it in terms of volume, which is what we want to solve for. And now we just plug in what we have. So we have 40 grams divided by 10 grams per centimeter cubed, and I end up getting 4. And as of course, for what? Well, in this case, our unit is centimeters cubed for volume. All right, so that's how you can do some of your density calculations. And what you will end up doing is all of this that we just did was for, so if you stop here, this is for 0, 2. So the assignment 0, 2, all of this information is going to be good for. It's just a lot of density calculations. Now, in terms of the pure substance versus mixture and stuff, and we'll actually stop before here, all of this stuff here is for 0, 4. Now we're skipping 0, 3 for some of you just because of the weather and all that fun stuff. But you have the slides here. I will kind of make some little interjections here and there just so that you have a better idea of kind of the terminology and stuff that I'm going to be using. So in terms of this, pure substances, elements, and compounds. Elements are what you see like on the element periodic table, right? These are the simplest form, form of matter that exists. And what we mean by that is that it cannot be broken down, right? So examples of this are just by looking at one of the elements on the periodic table. You'll get your periodic tables here eventually, but cannot be broken down. So this one would be an example is hydrogen. Right, we'll see what that 2 means here in a second, or iron, or chlorine, right? So anytime you see something that is just one capital letter from the periodic table, that represents an element. And how you can actually identify that is, let's say I had to draw a particle picture, which you're going to do here in 04, of H2. It's the same circles, right? If I said that, hey, each H is going to be represented by 2 solid circles, I could say then that this represents an element. Or if I wanted to do chlorine, so let me move this under hydrogen. If I wanted to do chlorine, I would say, oh, maybe I want to make it a nice little image there. For iron, let's say we wanted to represent it just by one circle. Regardless, what you notice is in all of those examples, there's only one type of circle because there's only one particular thing that we're representing. Now, even though this is H2, since there's only H's, that's why it's considered an element. Now, when we get to the compound down here, a compound is any combination of 2 or more elements chemically bonded together. Right? 2 or more elements. So in this case, examples of a compound would be something like lithium chloride or calcium oxide and things like that, where now I have more than one capital letter, which means I have more than one element that I'm dealing with. So if we wanted to draw pictures of these, I would just have to represent, say, lithium is a hollow circle and chlorine is a filled in circle, or calcium is a fun circle there, and oxygen is a filled in circle, something like that. But you notice that these combinations, these drawings, they actually have more than one type of circle, which means they have more than one type of element in there, which means that they are compounds. You can also have something like MgF2, where we have this 2 down here represents how many of those things exist. Now, magnesium, let's say, and you can just randomly assign colors and shapes to these. Let's say we want magnesium to be a hollow circle, and let's say we want fluorine to be a fun circle like that. Well, that 2 tells me that I have 2 F's that are connected. All right, but regardless, the compound idea is that those circles are not the same. Kind of like they were the same for the elements up there, they are not the same when they are attached to others, which makes it a compound. And then we have a mixture. Now, a mixture is any physical combination of pure substances. So we'll talk a little bit more about that idea of pure substances. What we just said up here was pure substances are elements and compounds when they are one particular substance. But a physical combination of pure substances would look like anything that has a plus sign. So in terms of like, let's say an example here is NaCl, which is salt, plus H2O, which is water. All right. Let's say that we have also, I don't know, C6H12O6 plus CaCl2. Right? Regardless, what we notice is that plus sign right here represents a physical combination. It's kind of like when we're in the classroom and we're all sitting in the same room together, we have a mixture of us, right? We're not all chemically interacting with each other and forming different things. We're our individual selves, but we are all existing in the same space, right? And that's what mixtures are. So we can say exists or existing in the same space. Look for the plus sign. Look for the plus signs and the formulas. An atom is the smallest unit of measurement, and you'll see what that looks like here shortly. Smallest unit of measurement. Molecules is any group of atoms together, bonded together. So like an atom would be, if I wanted to draw a picture, an atom would be something like this right now. For a particle picture, we'll get into what the actual atom looks like in a little bit. But this is an atom, whereas a molecule could look something like this, or it can look something like this, right? Where there's multiple atoms that are grouped together. Now they can be the same or they can be different. Does not matter, but as long as they're attached to each other, that's what we care about more. All right. So use the information up here for density to complete 0, 2. and then use the information that we have up here to complete 04. And I will also have video examples for each of those worksheets to help you out if this was a little bit overwhelming or a little bit too much all at once. All right. See you later.